Okay, so today we're going to be solving Griffiths problem 2.14 as it appears on the third edition of his book, Introduction to Quantum Mechanics. This problem asks us in part A to compute the expectation values of x, x squared, p, and p squared for the state psi0 and psi1, so the ground state and the first excited state. And it also says that it's probably helpful to use the change of variable that psi is going to be this right here and introduce a constant alpha, which is that right there. And I just set this little reminder of what each wave function was so that we don't have to go back into our notes and see what it is, because we already derived everything in previous videos. Okay, so let us begin by computing then the expectation value of x for the first for the ground state. So this is just going to be, as we know, psi0 conjugate x psi0 dx, right? So we have to now write our wave function in there. It's just going to be this m omega pi h bar, m omega pi h bar to 1/4, and all of this is going to be squared, right? But this expression is just alpha, right? This is just what we defined as alpha. So in order to not have to write all of that the entire time, we just say, okay, that's just alpha squared, right? It's just a constant, and at the end of the problem we can replace it by its actual value. Okay, and then we have this exponential. So we have x and e to the minus m omega divided by h bar x squared dx. In this particular problem, we are not going to use this change of variables because this is just an odd function, and an odd function integrated over a symmetric interval is just 0. So there's really no point in using that change of variables, right? So this is quite quick. If you're not sure why this should be 0, we made a few more examples in previous videos, and if not, it is always good to go back to seeing what happens with even and odd functions over symmetric intervals, because we will be using it a lot. I'm not kidding, we will actually be using it a lot. So it's really important that you know what it is and how it works. Okay, so now let's take a look at the expectation value of the momentum. Now this, I hope you remember, is just going to be 0. Why? Because this is a stationary state. Nothing ever happens in a stationary state. It's just there. And you can also see it if you take the momentum to be m times v, the velocity of the particle, which we can see as the rate of change of the expectation value of x dt. But since the expectation value does not depend on time, and in this case it's even 0, this is going to be 0. Okay, so you can also go ahead and do the integral if you want to check. But there's really no need for us to be doing that work in this particular problem, so we're just going to use these properties. Okay, so next comes the expectation value of x squared for n equals 0. Now this will require some work. So this is going to be alpha squared. Remember, that's just our constant of normalization of the ground state, but we just named it alpha, so we don't have to be writing that much. Then comes e to the minus m omega divided by 2h bar times x squared times e to the minus m omega divided by 2h bar. But since the exponentials and this x commute, we can just multiply them right away, and this 2 will cancel out. Okay, this is something we have done many times before, and this dx. So now let us introduce the change of variables that is that they suggest, which is that we create this variable called c, which is going to be, oh, by the way, there's supposed to be an x squared there, which is just going to be m omega divided by h bar, the square root of this, times x. And then the differential is going to be dxi, which is going to be m omega divided by h bar dx. And from here we can obviously see that we can find dx and x. So x is going to be just h bar m omega times psi, and also then dx will be the same thing basically, xi. Okay, so let us put all of these things into our integral. So we just get from minus infinity to infinity. The limits will be unchanged. Alpha squared e to the minus psi squared. And now instead of x squared, we get h bar divided by m omega times psi squared. and instead of dx, we get h bar m omega to the 1/2 d psi, right? So now we can just put all of the constants here up front. So we get h bar divided by m omega to the 3/2. And then we get this integral, which is just going to be psi squared e to the minus psi squared d psi. Now, this may look somewhat difficult, but well, there are several ways to do it. I'd say the easiest one is just to see, hey, this is just like the integral we saw in the previous video. Well, there was a beta up here, but with beta equal to 1. So let's now remember, let's call this I1. How did we solve such an integral? We just said, okay, if we derive this with respect to beta, then we will get what we have here. So let us take a look at this minus d beta, integral minus infinity to infinity of e to the minus beta psi squared d psi, right? Because if we were to do this derivative, we get exactly what is up here. In the previous video, I discussed this in more detail. So if you haven't seen that video and you don't know what's going on, I definitely encourage you to go ahead and watch that. It is even in the timestamp in the description, so you can just go ahead and look only at that part, because you really should know how to solve this kind of integral. They come very often in quantum mechanics and statistical mechanics and in other areas as well. So go ahead and learn that. So now this integral is just going to be a Gaussian, as we know. So this is going to be minus square root of pi divided by beta, and we have to take the derivative with respect to beta, the square root of beta. So when we do that, as we did in the previous video, that's why I'm going fast here, because we have already done this. We just get that this is going to be the square root of pi divided by 2 times beta to the minus 3/2 power. But beta is just 1, so this whole thing, this beta, is just going to be 1, so we don't even need to write it down. So this is our result. This integral is just the square root of pi divided by 2. So let us now go to the next page and write it in. So the expectation value of x squared is going to be alpha squared. I think it was h bar m omega the 3/2 power, if I remember correctly. Let me take a look. Yeah, that's what it was. And this is going to be multiplied now by pi divided by 2, but that 2 is not in the square root. So let me just fix that. Pi divided by 2. Just want to make sure that I didn't make that mistake before. Okay, great. Now let us put the value of alpha in here. Alpha is just going to be m omega divided by pi h bar and the square root of all of that. So now we will have several things canceling out. So this h bar and this h bar will cancel out, at least the square root part. Same with this and this. This pi right here will cancel out this square root. So what we get in the end is just going to be h bar divided by 2 m omega. Okay, that's going to be our expectation value of x squared. The integration was pretty straightforward, and as I said, it's not really necessary for you to actually do this substitution that is suggested. It is just so that the notation will be cleaner. You don't have to be dragging all those constants around. But if you hadn't thought of that and you didn't want to do that, use that constant of integration and that change of variables, I mean, it doesn't really matter, right? It's just going to be more things you will have to write down, but in the end, you should get to the same thing. Okay, so now we compute the expectation value of the momentum squared. So here we will have alpha squared, same as before, minus infinity to infinity. And now from this first, from this conjugate wave function, we can't really go ahead and write them together right away, right? We can't really multiply them, both functions, because there's going to be this operator in the middle, right? Because this is psi 0 conjugate, and then there's this operator in the middle, psi 0. When it was x, it didn't matter because x and these wave functions commuted, but now there is a derivative there. Okay, and we have to apply the derivative first. So we get minus h bar d by dx squared, bar squared, acting on minus e psi squared divided by 2 d psi. I apologize if my psi looks like something weird, but I'm not good at writing that Greek letter. Okay, So let us now put the constants outside, so minus h bar squared alpha squared. And now let us put in here what we already know for dx and dx squared. Oh, by the way, this shouldn't be the xi, my bad. We have not yet replaced it. It should be dx. Now we will replace it. So this is going to be the same. And in here, dx, as we saw, let me check where exactly we had it. Dx is just h bar divided by m omega. But we got d over dx, so this dx is in the denominator, so this is going to flip, right? So it's going to be m omega divided by h bar, and the square root is gone because this was squared. Okay, so then we get d dx, now it's xi, sorry, xi. And then we get e to the minus xi squared divided by 2, and this d xi will now be h bar m omega d xi, right? Just gonna double check that I copied it correctly. The x is h bar m omega. Okay, amazing. Add to the 1/2 power, the square root of that. So now we can just pull all the constants to the front, so we get minus h bar squared alpha squared, and then we get this m omega h bar to the 1/2 power, because they're going to cancel each other here. So this that was to the first power is now 1/2. Then we get the integral minus infinity to infinity e to the minus xi squared divided by 2. And now we have to derive. So let's derive one time. So we still have one of these derivatives here. So when we derive this, we are going to get we get this exponential times the derivative of its argument here. So that's going to be minus 2 xi divided by 2. So we can just rewrite it as minus xi e to the minus xi squared divided by 2. And then we get this d xi. So let us now go ahead and derive once more. Minus infinity to infinity e to the minus xi squared divided by 2. So now we have to apply the product rule. So first we derive this xi, so we just get minus e to the minus xi squared divided by 2, and then we have to derive the exponential, so the minus will cancel out and we get plus xi squared e to the minus xi squared divided by 2 d xi. Okay, so let me copy this so we can go to the next slide. Okay, so here we can do several things. Since we already used our derivative operators, we can now finally put the exponentials together. We can multiply them, so these exponentials will not be divided by 2 anymore, because it's going to be twice the exponent. Apparently I left my squared behind here. And we can now also factor out these exponentials. So what we will get will be, since we are going to factor in, we get xi squared minus 1 times the exponential, right? So we get xi squared minus 1 times the exponential of minus xi squared divided by 2, not divided by 2 anymore, d xi. Okay, so here we have two integrals. Let's call this one I1, this one I2. So the first integral is just going to be minus infinity to infinity of xi squared e to the minus xi squared dx. We already solved this though, right? We did this in the first part. It was right here. And we saw that its value is square root of pi divided by 2. So there's no need to solve it again. It's square root of pi divided by 2. The second integral, I2, without this minus, right? We are going to leave that minus outside for now. This is just going to be minus infinity to infinity of e to the minus xi squared dxi, but this is just a Gaussian integral. And we have seen this in previous videos. As I said, its value is well known. It's just square root of pi. Okay, that's amazing. So let's just put all of this into our expression for the expectation value of the momentum squared. So here we are going to get the minus h bar squared. Now I will replace the value of alpha squared by what it is. So minus m omega divided by pi h bar to the 1/2 times m omega divided by h bar 1/2 times what we have here. So And there is this minus that we can actually put inside, right? So we can now flip the signs of what is in here. So we get square root of pi minus the square root of pi divided by 2. So let's see, what do we get here? Many things will cancel out. So this square root of pi will cancel out these two square roots. So this turns into 1 and this turns into minus 1/2. Then we have h bar times h bar in the square root. So it will turn into a regular h bar, which will cancel out the exponent here. And so what we get is just h bar m omega times 1/2. So basically just h bar m omega divided by 2. Okay, so that's what we are going to get from this. I'm just going to double check that the result is indeed correct. M h bar omega. Great. So far so good. So as we can see, it isn't really too difficult of a process to calculate this. There's just a lot of integration that can be tedious, but it's not the worst thing ever. So let us now take a look at the first excited state. Let's begin with the expectation value of x. So let me, by the way, bring up the wave function for this because I don't really remember it. I don't know it by memory. So that is psi1 is a1 square root of m omega x e to the minus m omega divided by 2 h bar x squared. Okay, I think that's what it was. Omega to m. Yeah, I think I got it correctly. Yeah, okay. So let us now compute this integral as usual. So now when we conjugate this, as we said, this I, its modulus is just going to be 1, so it's going to cancel out. We get a1 squared square root of 2m squared, so just 2m omega squared times x squared e to the minus m omega divided by h bar x squared times x, right? Because we have to put the operator in there of what we want to find the expectation value of. So now, well, we can just put this x squared into this exponent right here. And now we just put all of our constants outside. So a1 squared, 2m omega squared. And now we can also go ahead and use our substitution, right? That we were talking about already before. Change x for xi. As I said, it's not really necessary. I'm going to do it because the book kind of suggests you do, so I want to show you how to do it. But if you don't want to do it, it's not really necessary. It will make the problem somewhat cleaner, so that is nice. Okay, so minus infinity to infinity. Now x squared will now be xi squared, cubed, sorry, it was cubed. And we have to multiply by h bar divided by m omega. So h bar divided by m omega to the 3/2 power. Then we got e to the minus xi squared, and the xi will be, dx will be the xi times h bar m omega. So what we will get now is a1 squared 2m omega squared h bar m omega. This is to the 1/2, by the way, and all of this will just be squared. So here, this omega squared will cancel out this right here, and this m will cancel out this squared on this other m. So let's just put it like this. So there we go. Okay, so now our integral is just going to be minus infinity to infinity of xi cubed e to the minus xi squared dxi. And well, now I feel a little silly that I did all this, because this is just, what is this? This right here is an odd function integrated over an even and symmetric interval, so 0, right? We could have just seen it here, to be honest, but I wasn't paying attention. And my dog just went crazy. Let me go open the door for him. Okay, sorry about that. let's continue. So we already found this expectation value of x, which could have gone a lot faster if we had seen before what it was going to lead to, but it's okay. So now we're going to see the expectation value of the momentum for n equals 1, which is still 0, for the exact same reasons as before, right? Nothing ever happens in a stationary state, and the expectation value of x dt is going to be 0. So, and as before, you can go ahead and check if you want, but it's going to be 0, so there's no need to integrate. So now let's go with the expectation value of x squared for n equals 1. So this is going to be minus infinity to infinity a1 squared 2m omega squared times x squared and times another x squared, which now comes from this operator, e to the minus m omega divided by h bar x squared dx. Okay, so this time it's going to be an even function, so we can actually work with this. Let us now pull these constant outside, 2m omega squared a1 squared minus infinity to infinity, and now we get psi to the 4th power times, what was it again? H bar divided by m omega. H bar divided by m omega, but it's the square root of this, so it's just going to be this quantity squared, e to the minus m omega divided by h bar, in which this whole thing, by the way, is as before just minus psi squared, and dx is going to be h bar divided by m omega d psi. Okay, so we are making progress. Now let's put all the constants up here, m omega squared a1 squared h bar divided by m omega. Now we got 5 divided by 2, right? So minus infinity to infinity, psi to the 4th power, e to the minus psi squared d psi. Okay, great. So what can we do now? We have to find a way to solve this. And well, now we are going to have to do some tricks. So what I would think of here, I don't know if it's the best thing ever, but at least what comes to mind is, okay, this is just going to be I1, and we want to solve it by integration by parts, right? Because if this were like an x squared, we would know how to solve it, right? And if it's x or x cubed, it's just going to be 0 because it's going to be an odd function. So let us now go ahead and say our u will be, let's say, x cubed, du will be 3x squared dx. Well, in this case, sorry, it's psi, it's not x. That was a bit of force of habit right there. So psi cubed, this is 3 psi squared d psi, and our dv is going to be psi e to the minus psi squared. That's why I picked x cubed, because I need to integrate something, and the only easy thing I could think of is something of this form, right? Because the integral of that is just going to be minus e to the minus psi squared divided by 2, right? That's the only easy integral I could think of here, so that's why I left one psi for the exponential, and the rest I put into this u. So this means that our integral I1 is going to be psi cubed times minus e to the minus psi squared divided by 2, evaluated between minus infinity and infinity. But this exponential will go to 0 much faster than the polynomial will go to infinity. So this whole thing is just going to be 0. Okay? So then we have the second term, which will be minus the integral of minus infinity to infinity of 3 psi squared. And then there's this minus out here, which will cancel out this minus. This will be divided by 2. And then we get e to the minus psi squared d psi. And will you look at that? That is something that we have already solved several times in this video. That is just going to be the square root of pi divided by 2. So we get 3 divided by 2 times the square root of pi divided by 2, which is just 3 square root of pi divided by 4. Amazing. So let us now put this into our expression for x squared for this n equals 1, the first excited state. So what we had was this a1 squared 2m omega squared. Then we had, I think, h bar m omega divided to the 5 divided by 2 power. And now this will be multiplied by 3 square root of pi divided by 4. Let me go back and check. 2m and then the integral. Okay, great. Should be correct. Where were we here? So, well, now we need to put in the value of a1 so that we can get somewhat of a simpler expression. The value of a1 is something that we calculated in a previous video, so we can just use it. So a1 is going to be m omega divided by pi h bar. And this is to the 1/4 power, but it's squared, so it's going to be 1/2 times 1 divided by h bar omega. And now we just put all of this here. So 2m omega squared h bar m omega to the 5/2 power 3 square root of pi divided by 4. Okay, so now we can begin canceling some things. So let's take the red pen out and see. Well, this omega will cancel out this right here. Then, well, this 4 here can cancel out this and turn into a 2. Then this pi can cancel out this. This h bar can cancel out this. Well, let's go. It's going to be an h squared, right? It's going to turn into an h squared. And then this h bar will cancel out that squared. So we will be left with an h bar down here. Then similarly, we got m to the 3/2 power up here and to the 5/2 down here. So we just are left with an m. Well, then there's the 2 from right here. What about the omega? We got similar situation here with the omega. Omega to the 3/2, omega to the -5/2. So we just get an omega down here. So we already covered this. Okay, I think we covered everything. So our final result should be, well, I already wrote it down. I don't know why I wrote it again. So this is our expectation value for x squared. Let me just go ahead and double check because it was a long calculation and oh, yeah, good that I checked. I forgot to put this 3 in here. 3, where are my 3h bar divided by 2m omega. Great, we're doing great. So this is our expectation value for x squared. I'm sorry if I'm going a bit fast, but there's a lot that we need to cover in this video. Well, you can always go back if there's anything that you did not quite understand. So let's go now for the expectation value of p squared for this first excited state. Now this will be the integral of -infinity to infinity of, as before, a1 squared 2m omega squared. And now comes e to the minus psi squared divided by 2 times psi. And now comes our momentum operator. So it's going to be minus h bar squared d by dx squared. Oh, by the way, I can't just go ahead and write this in here because I need to make sure that I multiply by the constant. So I'm just going to put x for now. This is going to be e to the minus psi squared. I can do this in the exponent because that's perfectly psi. I don't have to multiply by something to make up for it. Once again, dx and dx. It is kind of weird to just put some things in right away, but we're still in the process of putting our constants and variables in, so don't worry. So this is going to be a1 squared 2m omega squared. Oh, and I'm gonna put the minus h bar squared outside as well. So minus infinity to infinity of e to the minus psi squared divided by 2. And then there's this x, which as we know is just going to be psi times h bar divided by 2m omega. So h bar divided by 2m omega to the 1/2 power. And now in here we got d by dx squared. So this is going to be m omega divided by h bar d by d psi squared. There's a squared there. E to the minus psi squared divided by 2. And this x will be same as here, just psi times h bar divided by m omega. I put way too many parentheses. I think I need one more. And so this dx will now finally just be d psi times h bar divided by m omega to the 1/2. This should be a 1/2 as well. Okay, so now a lot of these h bars and m omegas are going to cancel out, so we get the same thing we had down out here. We haven't begun working with it yet, but now these h bar and omegas, we got the ones with the h bar on top, 1/2. Then we got another one right here, so it's 1 and 3/2. And there's one that is the inverse, but only to the first power. So in the end, we can take out h bar divided by m omega to 1/2. Okay. So now minus infinity to infinity, e to the minus psi squared divided by 2 psi. And now we have to apply the first derivative. So when we do that, we have to apply here the chain rule. Well, yes, but I meant the product rule, but the chain rule too. So this is just going to be, if we first derive this psi term, get e to the minus psi squared divided by 2 plus this other thing, which will be minus psi squared e to the minus psi squared and the psi. So let us now derive it once again. So we get, I don't really feel like writing it down again. So this whole thing. Okay, well, there's a little overlap there with the infinities. Okay, so now deriving this, we get with this first part minus psi e to the minus psi squared divided by 2. And from this, we get first minus 2 psi e to the minus psi squared divided by 2. I kind of forgot to write that down there. And then you get plus psi cubed e to the minus psi squared divided by 2 d psi. Okay. So here we got the same thing, minus psi e to the minus psi squared divided by 2 minus 2 psi e to the same thing. So we can just write it as minus 3 times this, and we can get rid of one of them. Okay, so well, now we can just go ahead and multiply, right? The derivative is gone. That was the thing that was causing us some trouble. So now we can go ahead and multiply and begin solving this integral. So this exponential here will now be just e to the minus psi squared. This is supposed to be squared. I apparently didn't copy that one when I copied. And then in here we get psi to the 4th power minus 3 psi squared d psi. Okay, but these things, well, I'm just going to go to the next page because I feel like it's probably good if I can explain this with some more room. So let's just go copy, go to the next page, paste, and I let it go. That infinity here is not supposed to be there. Okay, this first integral, let's call it I1. And the second one is going to be I2 without the minus sign, okay? So I1 is going to be the integral from minus infinity to infinity of e to the minus psi squared, what is psi to the 4th power d psi. But this is something we already solved somewhere. Let me see where it is. There it is. We solved it when we were calculating the x squared part, right? Okay, I kind of destroyed it there, but and the result was 3 square root of pi divided by 4. So there's really no point in calculating it again. It's 3 divided by 4 square root of pi. And the second integral is going to be, well, this minus 3 is just a constant. We are going to put it back later, but the integral itself is just minus infinity to infinity of psi squared e to the minus psi squared d psi. And this, as you will remember, we also did in this video, is going to be square root of pi divided by 2. So we can now put this into our expression for this p squared. And this is just going to be minus a1 squared 2m omega squared h bar divided by m omega 1/2 power times, now this is going to be 3 square root of pi divided by 4 minus 3 square root of pi divided by 2. So well, here we can put this minus sign in here so that these signs flip, and we can actually do this sum right away, or this subtraction, because this is going to be plus 3 square root of pi divided by 4. So we can put it like this. Okay, so let us now write down the expression for A1, which we actually did very recently. So let me just go ahead and copy it. It was m omega, okay, got it. So it was m omega divided by pi h bar to the 1/2 power times 1 divided by h bar omega. And everything else stays the same. I'm running out of space here, but I think we're okay. You know what? Now let's just go to the next page. I don't want to make too much of a mess. I feel this is already way too messy. Okay, so here we still have to put, this is e squared for n equals 1, and this is m omega divided by h bar pi to the 1/2 power, and this is divided by h bar omega. Okay, so we just put all the constants in here, and now we can once again begin canceling things out. So this square root of pi will cancel out this one right here. This 4 will cancel out this 2, and it will be just a 2. This h bar will cancel out the squared here. Then this will cancel this here, the omegas. And then on the top side, we got m to the 3/2, and here we have m to the 1/2. So we will just get m up there, and we cancel all of this. Then we have omega to the 3/2 divided by omega to the 1/2. So we just get omega. Then h bar to the 3/2 divided by h bar. So we can just go canceling all these things. We get h bar, and there's this 3, and there's 2. Okay, I think I didn't leave anything out. Let me just double check. So 3m h bar omega divided by 2. Okay, great. So this is our final result. So here we finished with the most tedious part of this problem. Okay, so the worst is over. We did all of these integrals. So, you know, congrats for you for keeping up. So now we are going to go to part B, because we already calculate all of the expectation values that we wanted. So in part B of this problem, we want to find the uncertainties. So let's begin for n equals 0, the ground state. The uncertainty of x. So what were our results? Let me go back and try and find them. Well, x squared was h bar divided by 2m omega. Remember, by the way, this is the square root of x squared minus x squared. But this x was just 0, right? So we just get the square root of our result here, which I already forgot. So let me just check. It was h bar divided by 2m omega. So we just get the square root of this. Yes. So our uncertainty for the momentum now, similarly, is just e squared minus e squared, but this here is also 0, just as that was. So what was our result? Let me go see. It was h bar m omega divided by 2. So h bar m, whoops, that was on the, yeah, m omega divided by 2, and the square root of that. So the uncertainty principle here is just the multiplication of these. So we get h bar 2m omega square root times h bar m omega divided by 2. So now, as we can see, m and omega will cancel out, and we get h bar divided by 2. So we can see that for the ground state, we are right on the uncertainty limit, right? Because the uncertainty, the principle of uncertainty of Heisenberg tells us that this has to be greater or equal to h bar divided by 2, and that is exactly where we are at. So great. Now let us check it for n equals 1. So sigma x in this case, let us go for x squared, because similarly as before, the expectation value of x was 0, right? So let me see, we're on page 6, so let's go to page 7. So it was 3h bar divided by 2m omega. So we were here at 3 h bar divided by 2 m omega, right? Just checking. 3h bar 2 m omega, yes. And sigma p, going back to the result we found recently. Where is our result again? There it is. It's just 3m omega h bar divided by 2. So square root of 3m omega h bar divided by 2. So let us now multiply this. We get sigma x, sigma p is going to be square root of 3h 2m omega, square root of 3m omega h divided by 2. And here the m and omegas will cancel out. And we get, let's see, so just 3h bar divided by 4, right? So, and as we can see, oh, sorry, not 4, 2, because of the square root. And this is obviously going to be greater than h bar divided by 2, so the uncertainty principle is obviously going to be satisfied. Okay, so now part C, which is actually somewhere down here. Oh, now I think about it. Yeah, part B was to check the uncertainty principles for these states. I don't think I mentioned that before, but that's what we were doing. I got a little bit carried away there. Part C asks us to compute the expectation values of the kinetic energy and of the potential energy. Okay, but don't worry, this is much easier than it is, okay? Because the expectation value for T, remember, T is just going to be 1 divided by 2m, expectation value of T squared. But we already computed T squared, right? So in the case for n equals 0, then the kinetic energy, the expectation value, will be 1 divided by 2m times, let me see what was our result for that. We are on page C. P was just h bar m omega divided by 2. So h bar m omega divided by 2. So this is just going to be h bar omega divided by 4. And in the case n equals 1, then this is going to be 1 divided by 2m. And this other expectation value was, I think, right here, 3m omega h bar divided by 2. 3m omega h bar divided by 2. So the m's cancel out. So we get 3 h bar omega divided by 4. Okay. Now for the kinetic energy, for the potential energy, the potential here in this, for this quantum harmonic oscillator is just 1/2 m, m is m omega squared times the expectation value of x squared, right? So let us now put in here the expectation values of x squared for each case. So for n equals 0, we get that this expectation value of the potential is going to be 1 divided by 2m omega squared times, so what was our result before? Let's just take a look. So the x squared was, where is it again? Here, h bar divided by 2m omega. So h bar divided by 2m omega. I think that was it. Let me just see. 2 cancels out that. So we get h bar omega divided by, let me see. Something here is not. Oh no, it's fine. That's exactly what we want. Okay. So, and the expectation value then for n equals 1 is going to be the same, 1 divided by 2m omega squared times the expectation value of x squared of the n equals 1 case. So let us go look for our result. Where was it again? A little bit, there we go. 3h bar divided by 2m omega. 3h bar divided by 2m omega. So here the omegas cancel out, the m cancels out, so we get 3h bar omega divided by 4. Okay, so these are our results, and we are asked to see if their sum is what we expect. So let's take a look at that. T plus V, this should be the total energy, right? Because this is basically the Hamiltonian, this is everything there is. So if we sum these for n equals 0, what do we get? We get h bar omega divided by 4, and then we have this other term which is the same, plus h bar omega divided by 4, which is just h bar omega divided by 2, which is the energy of the ground state, right? Because the energy n is just n plus 1 h bar plus 1/2 h bar omega, and if n is 0, we get h bar omega divided by 2, so that's amazing. And for the case n equals 1, well, what we get is just the sum of h bar omega divided by 2 and 3 h bar omega divided by 4, sorry. So what we're going to get in that case, let's see, oh sorry, it's, where's our second? There it is. It's 3 h bar omega divided by 4 plus 3 h bar omega divided by 4. So it's just going to be 3 h bar omega divided by 2, which is indeed the energy of the first excited state. So it was a lot of work, but here it is. We completed the problem to Griffiths 2.14, I think it was. And with this, we are officially done with the quantum harmonic oscillator, at least from the perspective of ladder operators. We will be back taking a look at the analytic part. So for now, just pat yourself on the back. This was quite a handful, so I'll see you in the next video.